So just to give an overview, I will describe the corrosion management principles, very briefly talk about effective corrosion management strategies, when we should start applying these, and then walk us through a couple of case studies, and then wrap up with a bit of a summary at the end. So effectively, what is corrosion management? Why should it be done? So corrosion management essentially encompasses a number of concepts which stand to underpin what degradation can happen to an asset and what will lead to that degradation occurring, be it from a corrosion standpoint, mechanical standpoint, or metallurgical standpoint. Then starting to look at how those damage mechanisms can be mitigated by selecting the appropriate mitigation measures and applying these correctly. Then measuring what has been applied in terms of mitigation, its performance, and how effective it has been, and feeding that back into a process, sometimes being an RPI process, so that the asset's integrity can be maintained, and then providing an opportunity for continuous improvement. The aim of doing this is to reduce risk, and how we achieve this is by reducing the probability of failure associated with a particular damage mechanism, because if you understand it and you can mitigate it, therefore you will manage it properly and you will reduce the risk. And if you have a high risk item that is in this location in the risk matrix, you start to drive the risk down. So that is the point of corrosion management. And in a nutshell, to achieve this, bits of corrosion engineering are thrown into the mix. So there are two different concepts. So what is effective corrosion management? Effective corrosion management is a practice that starts when an asset is being conceived or when a project is being birthed. The reason why it starts off at that point and starts becoming an effective practice is that you're looking at it from a design standpoint. How do you design out certain damage mechanisms? What specifications and standards do you have in place that help you manage some damage mechanisms? You assess those damage mechanisms from the get-go during the front-end engineering design, or feed as we call it. And then you start to select the materials and you start to look at what mitigations can be applied. You can either select corrosion-resistant alloys or apply coatings to slightly cheaper materials to ensure that they have that longevity in service. During construction, it has to be that the project controls must be in place to ensure that the items that have been carefully selected are constructed and put in place, following adequate QA/QC procedures. That starts to make things a lot easier to manage when you come to the operate phase. But the downfall of integrity management and corrosion management happens to be that a lot of companies start to think about corrosion management when they have already entered the operations phase. And at that point, it is leaving it a little too late, because what they dive into is what is really going on and how do we then start to put out the fires. Whereas you can have a corrosion management policy which sets out from the very top what the issues may be. You can have then policy documents such as corrosion control schemes, corrosion control matrices, which then point out the specific damage mechanisms, the precursors, and what to do when these may kick in the life of the asset. And all of that starts to set out what the mitigation should be, what the KPIs should be, how monitoring and sampling will occur. All of this then starts being fed back into an integrity review process, and then you have a robust understanding of what degradation mechanisms affect the asset. Needless to say, there are benefits of having corrosion management at the forefront of our minds when we start a project, because we start to see the benefits of loss of containment prevention very early on. We have life cycle cost reduction. So if you selected a slightly better performing alloy, you will have less downtime, less failure during the life of that equipment. And what that basically means is that overall you spend less. That also has a knock-on effect on the SHE metrics. So you start to see that your SHE metrics tick up. And of course, it means that we don't have to buy so many replacement materials. We don't have loss of containment into the environment. And that enables the organization achieve its sustainability goals, which is one of the big issues that we have at the moment. So I would like to create a quick poll here. I would like to see how many people think that corrosion management can be effectively applied to all damage mechanisms. So I'll leave some time to see what our thoughts are. Results coming in. Okay, so we're getting an uptake here. A lot of people are saying yes. So 14% are saying yes, that we can have corrosion management applied effectively. I'll just publish the results now. So you can see that there was a bit of variability, but about 33% have said that yes, it can be applied effectively to all damage mechanisms. 22% have said no, it can't be applied effectively to all damage mechanisms. An overwhelming majority has gone for yes with varying success, and no one has gone for unsure. So we're quite sure that this can be done. Corrosion management can be applied effectively to some damage mechanisms or most damage mechanisms with varying success. My personal take on this is yes, it can be effectively applied, but care has to be taken because not all damage mechanisms operate in the same way. And some of these damage mechanisms do not progress in a linear fashion. So sometimes they may be a bit more difficult to manage. However, yes, corrosion management can be applied to all damage mechanisms in an effective manner. So talking about corrosion control and management, how can this be done? As I've said, having identified what can happen from the get-go, you then start to look at what those damage mechanisms are, the key parameters driving them, and how you can stop some of these parameters from progressive corrosion. So here you can see that for sweet corrosion, for example, you have to control CO2 content, you have to control pH, you have to control temperature and flow regime. And how do you do that? You start to apply the right corrosion inhibitor, make sure that it is always available on the surface of the material. Ensure that you have a material that is in good order, and you start to ensure that you don't have any problems. You ensure that the surface is clean enough for the corrosion inhibitor to build the film on it. If you have an MIC problem, for example, you might then discover that you might have to do some flushing. So there are a number of ways to have all of this. For high temperature damage mechanisms, you will have to definitely rely on material selection, but understanding damage mechanisms is the key message here. Now, having understood those damage mechanisms, you need to understand the need to have key performance indicators. What then tells you that a damage mechanism is progressing and how quickly is it progressing? And the best way to do this is to have leading and lagging indicators. But one thing to note is that you should have a reasonable number of KPIs, and these KPIs should be weighted in an appropriate manner. Now, not all KPIs are created equally, and sometimes there's a bit more focus on KPIs specifically focused on certain damage mechanisms, or there might be system bias. That is, you might be looking at the more critical systems, whereas there might be a utility system that is also critical that can bring down all the operations. So there has to be that careful thought when KPIs are being designed. Now, as with everything, corrosion management doesn't come without its challenges, because a lot of people would wonder, how do we manage corrosion? How do we manage integrity? How do we monitor the degradation that is occurring, particularly if it is one of the more difficult ones, the higher temperatures, or you need to use non-intrusive tools? And how do you ensure that data you're collecting is actually accurate? As some of the other speakers will touch on, these may need to go into databases, and certain difficulties might be encountered. But in a nutshell, what needs to be done is to look at what improvements there can be to these sort of problems. So one way to do this is to conduct a gap analysis to see what specific needs the asset will require. You can do this very early on, perhaps at the design stage, and complete it just before commissioning. I've done that for a number of projects. And then we're in sort of industry 4.0. Now, where we are with that is that we are now starting to use more tools to understand the data we collect. So advanced analytical techniques, and that gives us a lot of data, and then we do analytics, or run analytics on that. Also, auditing the databases that we have is a very key part of what needs to be done, and engaging with management to get buy-in. So establishing that we have a link to the performance of the business, showing that there is impact on the bottom line balance sheet. So if you can show that there are reliability losses, I think everybody in management will be able to sort of identify what that really means for the business. So I'll move swiftly on to some case studies. And the first one is a CUI of a naphtha line that occurred in a refinery in Norway. Now, this was a 4-inch line that was circa 50 years old when it failed. One of the key issues which I've highlighted as part of the first part of the talk was the integrity of the data that was in the database. So this line existed in SAP, which was used as the maintenance management system, but was removed. And during an audit, about 5 years later, it was found that that line had been removed, but that error was never corrected. Now, that meant that that line never got scheduled for inspection after 2008. And even when the rest of the circuit was inspected in 2018, the line was not looked at. There were no visual checks, there was no line walk, and it meant that when the line failed, it was unexpected. A lot of people were working in the area, and this is a plot of or a map of the refinery showing where the failure was. And those people were exposed to a fire hazard, although, to be fair, the material went into an open drain system, but if it had caught on fire, a lot of people may have been harmed. And these people also did not have the right kit, and they were exposed potentially to a carcinogen. So this is just a plot showing exactly where the pipe existed. So it's in a critical part called the pipe still, or the distillation system, as you can see here, and that was where the leak emanated from. Why was this missed? This was missed because there were no lessons learned from previous CUI failures. There was no understanding or no deep dive into what surface protection was applied from the very start. And this is the primary barrier for CUI management. They do when they installed it, no robust checks regarding the QC measures put in place at the time. And of course, as we know, installation methods for coatings and the coatings themselves have moved on in time since when this was installed. What was found during the inspection were the progressive checks, reports giving about cladding condition. Nothing was found to suggest that this occurred. And what was the understanding regarding the degradation, the the rate at which the material corroded, the pipe corroded. Looking at the lifetime of that pipe, it should have corroded at about 0.1 millimeters a year, but that would have meant that the coating was ineffective from day one. So it meant that the pipe existed for some time, and later on, CUI started to sort of take off in terms of rate. So the corrosion rate should have been much greater at its peak, much greater than 0.1 millimeters a year. So establishing what the boundaries should be for acceptability is key. Understanding what the barriers are to prevent CUI would have helped in mitigating this leak. So as I've just touched on, understanding when fabric maintenance should have been carried out is something that should have been done. That's a key performance indicator that could have been put in place. There is guidance in ISO 4628 Part 3 and an Energy Institute guidance on external corrosion. So the combination of the two documents is what's summarized in this table here, and different organizations have different ways of using this, but the key takeaway here is that you should have a threshold beyond which it will be unacceptable to continue with a material that is corroded in service. Also, it should be that CUI assessments should be completed, particularly for lines that are of the nature this was, because it operated at 90 degrees, and that is in the prime CUI range. So assessments for lines at high risk of CUI should be completed, RBI should be updated, and that should then start to inform how much inspection should happen, techniques that should be used, and start to feed back into the management, corrosion management process. Of course, if the inspection database was interrogated properly, then it would have been found that the inspections were missed. And it would have been found that the last inspection was more than 14 years ago, so it would have prevented that failure. And that also ties into the remaining life bit, which I talked about earlier. So the second case study is perhaps one which might interest some of the people on the or some of the listeners here, and this is MIC of a natural gas pipeline that occurred in the US. So this natural gas pipeline failed in service after about 50 years, and it was a very prominent pipeline that took natural gas from fields in Texas, such as the Permian, all the way through to the California market. To give a sense of scale, there were about 60 compression stations and along the way 300 compressor units. And that was a lot of gas that was being fed into about 4 states and into Mexico as well. When this failure occurred, there were 12 fatalities in a space of an hour, and that there was a massive fire. As I will show in the coming slides, it was as though a bomb was detonated in the area. And the company didn't think much of it at the time. They only thought that this was going to set them back about $1 million USD, but it was much more significant than that. So this is the fire, snapshot of the fire that occurred. As you can see here, that's the height of the bridges used to suspend the pipelines across the Pecos River where this failure occurred. And that's a fireball which can be seen here. So the height of the fire at its highest was about 150 meters. The people who ended up as fatalities were camping at this very popular but rural campsite near the pipeline. And at the time, it wasn't thought that anything could go. And they were all consumed by this, so there were no survivors. Initially there were survivors, but everyone happened to be a fatality, and they were all from the same family, so it was really tragic. So that there is the crater that happened after the rupture of the pipeline, and this map shows the sort of locations the pipeline traversed. Why did this happen, and could it have been worse? So as you can see, there are 4 pipelines here. 3 were in service, 1 wasn't, and those pipelines could have also been affected. These pipelines were all linked, but there were 3 things that really led to this tragic event. First, the regulator had inspected the company to find out whether they were looking after the pipeline correctly, and they didn't find anything wrong for many years. But following the incident, they then did a robust check and they found several failings in the system. So is it enough to expect that the regulator gives you a tick mark, or are you going to self-regulate? The pipeline also was designed quite poorly, which didn't lend itself to any cleaning or internal inline inspections. And therefore, internal corrosion management was really, really difficult and really poorly done. Essentially, what happened was that no cleaning pigs were run for the first 25 years. And later on, when pig traps were retrofitted to the line, the entire line could not be cleaned. This gave rise to the opportunity for microbes to thrive and proliferate because there was low gas velocity in some areas, sludge accumulation, and of course there was water associated with the gas. And this schematic here shows what existed. So there was a massive dead leg here, and that dead leg used to be drained into a storage tank. So the fluids would collect in the dead leg for a long time. And it was a section not too far from this location that had a lot of thinning and the eventual failure. Another issue was that the weld that failed was at the bottom of the line, so it was preferentially attacked, and there was a significant loss of thickness, over 70% at that location. Why did this happen? Microbes were in the mix. And when you have microbes that have established themselves, you have this sort of biofilm in place. Underneath the biofilm, you can have corrosion happening, and that gives rise to these sort of ridge-like structures or pits that you see. The local environment there is really rich in nutrients and chlorides to help the microbes thrive, and these microbes coexist because there will be different forms of or different types of microbes in the mix. So with a low pH, the microbes established a really firm colony and caused this corrosion and thinning of the line at the bottom. Was it that the pipeline operator wasn't looking at the pipeline? Certainly not the case. They had looked at it externally. Internally, the data that was collected had to do with whether or not they met the water cut, which is something I talked about. So for the most part, they met their obligations, but there was still water in the line, meaning that they could have microbes thrive. There was still sludge in the line, and they noted this from several pigging runs that were done in the later life of the pipeline. In 1999, about a ton of solids was removed. When you have that significant an accumulation of material, then you should consider doing taking some really stringent steps to mitigate that. But unfortunately, none of these were significant enough KPIs to make them have a rethink about the integrity of the pipeline. Although they collected data and ran some cleaning pigs, they didn't look at the data correctly. They didn't do any sampling or microbiological analysis to understand what was within the mix, and there was no corrosion monitoring that occurred. In the end, the lesson that was learned was a huge one, because they were about to spend 90 million, or they had to spend 90 million USD on corrosion management for the entire pipeline that they ran, and they ran about 10,000 miles of pipeline across the US. So they had to ensure that all their pipelines were fit for service, and they found others that failed in service when these retrofits were being done. And they were hit with a $15.5 million fine because of the extent or the severity of the event. So having the wrong measures in place or not having a corrosion management policy could be a very, very costly mistake. What could they have done differently? They could have analyzed the microbial samples and the pig trash using traditional methods, which would have told them what they're looking for, so things like MPN, or they could have used molecular methods. In today's world, we can actually use molecular methods such as qPCR that tell us everything about the spectrum of microbes that we have within the mix. And with that, you can then start to set some key performance indicators and know when you should apply a biocide to kill those microbes. And you can even have targeted solutions. So what is the learning here? Corrosion management should start during the design phase of a project. If your projects typically don't have that incorporated, then you should either engage with the EPC contractor, speak to them and have somebody within that organization to assist with it, or within your own organization, have the competent people who would be able to support this. During the operational life of the asset, this should also be supported in-house by people. If that is outsourced, you have to make sure that they have the right competencies and they work well with the organization. And there is constant communication about the key performance indicators and what they mean. A firm understanding of the plant is also necessary, and understanding which process parameters tie into key performance indicators will then start to set out what is happening regarding the integrity of equipment. And there should be a defined process through which all of these threats will be managed. So typically this occurs or is written up as a corrosion management strategy or policy document. All checks should be done when modifications are conducted on site. And all of this, when done, will then yield the continuous improvement that is desired. And that way we'll be able to achieve the aim, which is making sure our equipment lasts longer and keeping the fluid within the pipe or within the equipment.